All right, 2.2, we had left off on talking about sets. And in particular, the last thing that we had done is we had referred to something called cardinal number, and we were finding some cardinal numbers. Cardinal number, if you remember, is actually just the number, find out where it was, the number of elements in a set. It's just how many of them are there, okay? And we were looking at some sets of numbers when we left off on. We had done A, which was set A, and we figured out that we would take the 99 at the end. We would subtract the number that was before the one we were working on in our sequence at the beginning, which was an 8. And we found out that there were 91 elements in the set, so its cardinality is 91. All right, set B. So we're doing n of B now. Remember, this notation just means number in the set. That's what that n is standing for, n for number. And we have a set kind of like the last one, except that it's not every number, right? It's skipping some, right? And we've got 2, 4, 6, 8. It's the evens. So how can I figure out how many are here when they're not all here? We've done this before.
Divide by 2.
We divide by 2 because it's skip counting by 2s, right? Now, we are going to divide something by 2. We have to be a little careful. This one's not bad. It's just 2,000 at the end, 2, right? The 2002 divided by 2. But that's because it actually started at 2. So in general, what we're going to do is we're going to take that ending number, and we're going to subtract, again, the number that came at the beginning, and then in front of that in the sequence. So what comes before 2 in the sequence of even numbers?
1.
Not 1. 0. Yeah, so it has to be in our sequence, right? 1 is the number that's before it, but it's not even. So what's the number that comes before 2 in our sequence? And you can kind of think about it as counting backwards, right? If I counted backwards, what would come before this? And that's not a good color. Let's try that again. Different screens. It would be a 0 that would come before my 2, right? Because it would be adding 2 every time or subtracting 2 if I go backwards. So that's why here it's really not affecting it because it's 0. So what we get then is 2002 divided by 2, which is what? 1001. If ever in doing this, kind of like with Gauss's, you get a fraction or a decimal, it means that you've probably subtracted the wrong thing. So if we did accidentally subtract the number 1 here, we would have had 2001 divided by 2. Well, 2001 divided by 2 is going to give me a decimal kind of an answer. Well, there can't be a decimal number of numbers here. That doesn't make sense, right? Just like you can't have 0.5 of a person. You can't have 0.5 of a number either. It just is a number. It's countable. All right. What about this next one? So it looks really weird. It says, it's a set notation that we talked about last time, a set builder notation. It says these are all the x squareds such that x is equal to 1, 3, 5, up to 99. So let's first of all just write down what this set is, because this set is in set builder notation. And I'm going to write it again in listing method. So this tells us that we're going to take the first one, which is a 1, and we're going to square it. It's 1 squared. Then we're going to be taking the second one, it's a 3, and we're squaring it. And the third one is a 5, and we're squaring it. And we keep doing this until we get to 99 squared. That's what this set is. Now, does the squaring affect how many numbers there are? No. It doesn't affects the value of the numbers, right? Obviously, 99 squared is not the same as 99. I get that. But it's still just a single number, right? 99 is a single number, 99 squared is a single number. It's just the same number of numbers. So what we are left with counting when we're counting how many are here is the same thing as what we would have counted if we'd counted them before we squared them. How many are here? Well, it's not evens this time. It's actually odds, right? It's odd numbers. And we can do the same thing that we did in the last situation. So this is n of c. We can take our ending number and we need to subtract something. We're skip counting still by what? Odd numbers, but what is the number by 2s? We're still skip counting by 2s, like we're going every other number, right? It's just that they're odd instead of even. But it's still skip counting by 2s. You can think about what we did when we were looking in section 2.1. If I go from here to here, I'm still adding 2 each time, right? That's what skip counting means. I'm skipping something. I'm skipping that one number in between, skip counting. So it's still dividing by 2. But I need to subtract something. I need to subtract the number that comes before the first number in this sequence.
-1.
It's -1. Does that make sense to everybody? Right? If I were to go backwards in this list, what would come before 1 if I go backwards? Instead of adding 2, I subtract 2. I'd have -1. Now, what happens when I subtract a negative? It's positive. So how many do I have? What's my value on top? It is 100. And what's 100 divided by 2? 50. Now, does that make sense? If I had all of the numbers from 1 to 100, how many of them are odd? 50. How many of them are even? The other 50, right? I realize this stops at 100, but putting the number 100 in my mind doesn't change it because it wouldn't really be in my list because it's an even, not an odd. So there are 50 numbers that are odd between 1 and 99 or 1 and 100 if you think of it that way. Okay, what about the last one? Set D. This says, I want the set of all x that satisfies this equation. X is equal to x plus 1. All the solutions of the equation, x is equal to x plus 1. Well, what values do you know that satisfy this equation?
It's a natural number.
It's got to be a natural number. What number would it have to be? Or what numbers could it be?
1, 2, 3.
But do those work is the question. So let's take an example of that one. Let's just take the number 1. If I put the number 1 in for x here, is the equation going to be true? Nope. I'm going to get 1 on the left. I'm going to get 2 on the right. So 1, while it's a natural number, doesn't solve this equation, right?
No solution, right?
There's no solution. Thank you so much. I don't know how long I would have waited. Thank you, Ty, for not making us wait any longer. There's no solution to this. I cannot take a number and add 1 to it and get the same thing. Right? Right? If you take yourself and you add a sweet mate in your sweet, you no longer have just yourself in your sweet. Right? You can't add something to it and not make it change. This has no solution. There's no solution to this equation. So how many numbers are in set D? 0. This is a null set. Now, this still says 0 because it's saying I want to count the number of objects in the set, and the counting number is 0. But this set is the same thing as the empty set, so I could also write, not that I'm asked to, but just as a reminder from notation from last time, that this is equal to the empty set. That's that empty set notation. Okay, so that set is the empty set, the set that has nothing in it. We counted it, there's 0 items. All right, so let's take a look at what happens next. We're going to take a look at something called Venn diagrams. Venn diagrams are used to illustrate ideas in logic. In a Venn diagram, there's a universal set, and I'm going to draw a picture in here. I don't have a lot of space, but it's a rectangle. They always draw the universal set as a rectangle, okay? And it's going to contain all of the objects under consideration, all of the elements that are in our discussion. So perhaps our universal set is this classroom, okay? You know, the people in this classroom would be our universal set. Well, we would all be in the box, okay? And then within the set, the universal set, there are typically other smaller groupings of things, and they're done in circles. So perhaps in this set that I've drawn, because we have both boys and girls in this class, we can do this. We can actually use that this circle set is our girls, and then the part out here would be the guys. Okay? So we're distinguishing it in two separate places. We can make anything a distinguishing factor. We could do your age, right? The circle in the middle is a certain age and up, and the circle on the extra on the outside is a certain age and down. You can do that. You could do how far you are away from home, right? We could do that. So there's a distinguishing factor somehow that separates the things that are in the circle from the things that are outside the circle. Does that make sense? The inside of the circle is called another set. It's a set, right? And the stuff on the outside is the complement. Okay? So this set that's here, let me take off my notations so that I can put the names in that it's given down later. The circle in the middle is what they're calling set F. And this part here on the outside, I'll draw it in yellow and then I'll label it, is the complement. And your book uses a notation, I want to make sure I use the right one, with a bar on the top. Okay, that is different than the contemporary math curriculum that we use, by the way. So beware if you've taken that class. It's got a bar on the top. So this notation out here is known as the complement. It's got a bar on the top. I do want you to know some other notations you could see show up, because if you did see them in some other book and you were like, that doesn't match mine, you should at least know they're meaning the same thing. So our contemporary math book uses a notation of prime. Do you remember that one, Anna? Yeah. There's some books also that use what looks kind of like a subscript that's a C, which is actually kind of friendly because it means complement for C, so that's kind of nice too. But we're going to be using in this class, this first one, that's what you'll see used everywhere, okay, the bar on the top. So complement, it means everything that's not in whatever this descriptor is for the circle on the inside. So we're going to do an example where we're going to describe what the complement is. So we're going to say that our universal set, that's that big outside rectangle, is the set of all students at OBU. And then set A is those who are graduating. What would a complement be? Don't overthink this. Those who aren't graduating. We do probably need to specify still that we're at this, we're talking about the students at OBU. So these are the students at OBU. Who are not graduating. I think that's all of you guys right now. Nobody's graduating in December, are you? Not yet. So you're in this category, right? You're in the A complement category right now. So OBU students who are not graduating. Now, you can also take some sort of a descriptor, and you can define even more, like narrowly define it further, right? And so when you do that, you create something called a subset. So for all sets A and B, we would say that B is a subset of A if and only if every element of B is an element of A. And the way that we write that is it looks like kind of like a U on its side, or kind of like a squished C, right? It's like a flat kind of a C, and it has a line underneath it. It means every element of B is also in A. Okay, everything in B is also in A. So here's an example. If I describe my family, and I'm talking about, so my husband and I and our downline, right? Like the children in our family after us. Right? If my mother described the same grouping of people, it would include myself and my children, my husband. It would include all of us, right? Because I have some brothers and sisters and they have some children, it would be bigger than just that. So if my mom said, my children and grandchildren, my family, she'd be including all of us because she's talking about the people going down from her. And if I did that, it would include me into her set. Everyone in my family is in my mom's family. Okay, so my family is a subset of my mom's family. A proper subset is actually what I just defined. A proper subset means it's a subset and it's really smaller. And so it says for all sets A and B, B is a proper subset of A if and only if, that should say if and only if. B is a subset of A, and there is at least one element of A that is not in B. The notation for that looks the same, but it excludes the equals underneath. What it's saying is that it can't be equal. The first one could. So now imagine that my mom did this again. She's talking about all of the children and her grandchildren, right? Her family, all of her family down. And she's talking about the family down, and I'm talking about all of my family that would include me. If I were an only child, we'd be talking about the same people, right? Like exactly the same people. There'd be nobody any different. I'm not, so it doesn't work that way, but imagine that I were. Well, those would just be descriptions that are the same people. They're the same sets. They're just being described a little bit differently. But the definition we encountered first would still hold. Everybody in my family is my mom's family, right? That works really well when my husband and I describe ours, right? So if I describe all of my children, my husband describes all of his children, those two groups are the same children. We share all the same children. So if we describe things that way, you could say, well, all of my children are his children, so my kids are a subset of his kids. But it sounds funny because they really are equal, right? So the first one is actually telling us they could be equal. That's why you have the line underneath it, kind of like less than or equal to. It could be equal. They don't have to be, but it could be equal. But in the second one, proper subset, it's telling you it can't, right? There's this other set that's actually got something else in it. In this case, it would be my sister or my brother and all their children. Those would be the extras in my mom's grouping that she's describing that wouldn't have been in mine. And there's a way of figuring out how many subsets there are. So if we have a set within elements, then there are 2 to the power n subsets. And there's 1 fewer than that proper subsets because we throw out the set that's got everything. Okay? So 2 to the n subsets and 2 to the n minus 1 proper subsets. And we're going to do an example. So we're going to consider the set of all mathematics faculty members at OBU. If you don't know all of us, there's 4 of us right now, full-time. We have a couple adjuncts as well. But there's 4 full-time. And a subset would be some sort of a grouping of people to do something. So imagine that you wanted to create, committees, right? This happens all the time. People create committees. I'm on the teacher education committee. So did I have any of you in my interviews? I don't think so in this class. I did some in my other class where I did some of the teacher ed interviews. Okay, so I'm on the teacher ed committee. Well, let's say we wanted to create a committee within just the math department. It's just going to be math people on it. Well, you could have a committee that has everybody on it, right? Everybody could be like, it's the full committee. You could have committees that have 3 people on it, right? You could do 3 of the 4 of us on a committee. You could have groupings where there's 2 of us just on a committee. You could have groupings where there's just 1 of us, right? We are the only one that's assigned to do X, Y, Z. We are the committee. That'd be a funny way to describe it, but it's a grouping anyway. Or you could have a group that has none of us on it. Right? We just are not represented in any way, shape, or form, or we're not doing that activity. It's the empty set. So if we're wanting to figure out how many subsets there are, we'd have to list out a lot of things, right? We'd have to make a list of each individual person. And then each other person paired with each other person once. And then we'd have to do all the pairings of 3 of us together. And then we'd have to do the pairing that has everybody and the pairing that has nobody. And the bigger the number, because there's only 4, this wouldn't be terrible, but the bigger of the number that you're talking about, the more different listings you'd have to make. Does everybody agree that does not sound like fun if it gets much bigger than 4? Yes, Caleb agrees. Thank you, Caleb. I don't think it sounds like very much fun. And so we have a way to shortcut that system, and that's this number of subsets theorem below. So it says that I can take 2 and I can raise it to the power of how many elements there are. Well, in this case, the elements are the math faculty members, and there's 4 of us. So what is 2 to the power 4? Not 2 times 4, but 2 to the power 4. 16, you got it. There are 16 different groupings or subsets of the math faculty, and that's only 4 people, okay? And one of those is going to be the entire group of this. So if you take that 2 to the 4th and subtract 1, you'd have the 16 minus 1. You would have 15 that are proper subsets. In other words, they don't include everyone. Okay, listing out 16 groups or 15 groups wouldn't be terrible. But if you had 5 members of the math faculty, which we did at one point, OBU was a little bit bigger. We had 5 faculty members. We will in about a year from, not a year from now, but 2 years from now, there's going to be 5 math faculty because we are going to have a higher need because we're teaching more math classes due to the engineering program. When we have 5, what is 2 to the 5th? 32. I don't want to do 32 items written down. Push comes to shove, 16 is not so bad. 32, that's getting to the point where I find it really annoying, right? I don't want to write 32 different things down to list all these out. So this is a very handy theorem Now you can use this theorem in reverse as well. This says, suppose you have a set about which you know there are 63 proper subsets. Okay, they're telling us the number of proper subsets. Okay, so what is the equation for proper subsets that we just looked at? 2 to the n minus 1. And it's telling us there are 63. Now, this is going to be a nice number, so you don't necessarily have to solve this with algebra. You can do a little bit of quick trial and error to figure out what n has to be. The first thing I'd probably do, I probably would add the 1 because I find that a little annoying. So 2 to the n equals 64. And then I can try some things. And you go, well, what is it? Maybe it's 2 to the 10th. And you try it and you're going to find it's way too big. Right? And you can play with that a little bit. What number is n in this one? It's 6. N is 6. Okay? And I'm just suggesting trial and error. And your calculator can be the tool by which you do the trial and error. Okay? So if you take 2 to the power 6, your calculator will tell you that that is 64. So we have we have 6 elements in the set. There are 6 elements in this set. Okay. So we have this symbol. I'm going to flip back over here for just a second. That's got a sort of a squished C, a compacted C with the line underneath it. And it is a subset symbol. Sometimes I will read it as is contained in. That's not a great notation because I say that for elements too, is contained in. So try not to. But they are both contained in. It's not an inaccurate statement. It's just not real informative because it could mean either one. But what we're going to be looking at over here is deciding which statements in which situations work. So you notice this one's the element symbol, right? And I've got the exact same questions over here, but this one has the symbol with this contained in that's a subset symbol. Does everybody see the difference? So the next 2 examples, example 7 and 8, look exactly the same, except the directions have the tiniest bit of difference, and it's the very top with the symbol they're telling us to put in there. This one's got that symbol, and this one's got this symbol. Now, when we're looking at this first symbol, element of, there's 2 things we have to check. First, we need to check and make sure it's really an element, an individual item that's in the set. So if you look at letter C. Letter C will automatically fail to be an element of what comes next because the notation on letter C has curly braces around it. That curly brace notation means that it is a set. So C is going to fail to be an element of because this isn't an element at all. Right? It's not even under consideration. It's like if you're doing a job applicant pool and they tell you have to have a master's degree and somebody sends in their paperwork and they only have a bachelor's degree. They don't even get to be considered. They didn't meet the requirement of the first step, which was you got to have a master's degree to have this job. Right? This fails to meet the first criteria of even being an element at all. It doesn't matter if it's one of the things described over here on the right-hand side. It's not an element. Does that make sense? So that's one thing that we have to consider. There's one more that fails for that same reason here. And we do slashes through things to say that they're not in it, right? So this is not an element. There's another one on here that fails to be an element. Which one is it? A. Remember that notation? I mentioned it last time. I've brought it up this time. What is the thing that's on the left called?
Is it null set?
It is a null set. And even in its name, you hear the word set, right? The null set is a set. It is not an element. So it can't be an element of whatever comes next because it's not an element at all. Okay? So this one fails because it doesn't fit the very first criteria. It's not an element to begin with. So the last 2, B and D, at least stand a chance. They're elements. They're individual objects. They have a fighting chance at being able to put that element symbol and not put the slash through it. So the second thing we have to consider as we look at these are they being described by the thing on the right? Are they really one of those objects? Right? Are they really one of those things? So on letter B, this says 15 on the left. What kind of numbers are being described on the right? Well, it's set builder notation. It's not just a listing, right? So we do need to be a little bit careful that we understand this description. This description says, whoops, I'm in a highlighter there. This description says that we're looking for elements that are 2 times the natural numbers. Okay, what are the natural numbers? The counting numbers. 1, 2, 3, 4. What happens when you take those numbers and you multiply them by 2? What do you get? 2 times 1, 2 times 2, 2 times 3, 2 times 4. What do you get?
Natural numbers.
Nope. Well, they are natural, but there's more. There's a better description than that. What are they? They're even numbers, right? If I take the natural numbers, I'll make a list real quick of a few of them. 1, 2, 3, 4. And I multiply each of those by 2. I get 2, 4, 6, 8. They are natural numbers, but a better description is that they're even, correct? Okay, so this set over here is a way of describing even numbers. Okay, so 15, check mark the first box. It's an element. But isn't it an element that's being described by the set on the left, on the right? No. 15 is not even. So this one fails, but it fails for a very different reason than A and C failed. A and C failed because they actually aren't elements at all. B failed because while it's an element, it still didn't meet the criteria that was being described. Okay, so back to my example real quick of the master's degree. A and C failed because they didn't have a master's degree at all. B failed because it had a master's degree in the wrong thing. Right? It met the criteria of master's degree, but it wasn't in the right field. Okay, so it failed, but it failed for a very different reason. Yes? Candidate did not get the job. All right, the last one then. 16. Okay, we've got the element 16. It is an element. Yeah, definitely an element. Is it going to be in this list that continues on ... It is. So this is a listing method of the same thing that B was, correct? But it lists it out this time. And 16 is one of those objects. It's an even number. So this one actually is an element of. Okay, so 16 is an element of what comes on the right because it's an element to begin with and it's being described by what's over there. Okay, now we're going to change the question that's being asked. All the same pieces are there, but the question's different. This question wants to know which ones are subsets. Okay, so no longer am I wanting to have an element. In fact, if I have an element, it's not going to work. An element is not a subset. So B is not going to be a subset of what comes next because it's not a subset at all. And D is not going to be a subset of what comes next because it's not a subset at all. Right? So different ones fail from the get-go because the condition of what I'm describing changed. Okay? So 15 and 16 do not work. A and C stand a fighting chance because they are sets. The fact that they are sets means they could be subsets of what comes next. Everybody good so far? Now, this is the first time we've talked about subsets in this way. Subsets, again, meant that everything in the group on the left is also in the group on the right. So, the first one here, A, is kind of the odd one, and it feels a little odd, but I bring it up because you need to know that it always does this. Every element in the empty set, of which there are none, is always an element of what comes next, no matter what's on the right-hand side. This one is a subset. It doesn't matter what's on the right-hand side at all, not in the slightest. It's kind of one of those like you got in by default, right? You made it in the door because you were related to the guy who was throwing the party. He didn't really want you to come, but you were related, he couldn't kick you out, right? But that's what's going on here. You get in by default. There's nothing in the empty set. So everything that's in the empty set, right, air quotes, everything that's in the empty set is going to be in what comes next because there's nothing there to start with. The empty set is always a subset of every other set. Now, the one that's more interesting than to talk about is the one that's C. It's a set. It's a set because of the curly braces, okay? So again, meets the first criteria. It really is a set, so it might be a subset. And the question is everything in that set, so what's in the set that's on the left this time? Just the number 4. It's the only thing there. Is everything that's there, i.e. the number 4, also in what's being described on the right? It is. And in fact, what's being described on the right looks a little bit funny, but could we write it in a nicer way? Sure we could. What elements are over here on the right? 3, 4, 5, 6. So feel free to take weird notations and just write it in a way that's more accessible. Is everything in the set that contains the number 4 also in the set that contains the number 3, 4, 5, 6? Yes, because the one thing that's there is in what's on the right-hand side. Okay, everybody good so far? All right. The next one is something that shows up, and it shows up again in proportional and statistical reasoning as well. It's called the fundamental counting principle, and we encountered a little bit of something with this when we talked about one-to-one correspondences before. It wasn't a fully fleshed out item, but it was what we were encountering there. The fundamental principle of counting, or the fundamental counting principle, says if you have two events, you have event M, and it can occur in little m ways, and you follow that by event N, and it can occur in little n ways, then the total number of ways that event M followed by event N can occur is in the product. Okay, it's the product of those things. We did this when we were doing the example I gave verbally. It wasn't written down this way. It was going to a dance, I think it was. I don't know if I described it exactly that way. And there were 6 men and 6 women, something like that. We said, how many ways can the first guy choose somebody to date with? And we said it was 6. And then we said the next guy was 5 and so forth. And at the end, we multiplied them all out. We were using the fundamental principle of counting to do that with the one-to-one correspondences. We can do this with lots of examples. And so the one that I like to do on this one, for some reason, is outfits. I think it works really well for this. So we're going to assume either number 1, that everything matches and we're okay with that, or number 2, it just doesn't matter if we match, okay? So this is not an issue of whether or not the outfits actually look good, okay? Think about the 4-year-old that just thinks they look great no matter what they put on. Think about them, okay? All right, so we have how many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes? Well, there's 3 different things we're choosing from. And I always write these down kind of in space bar holders. So this is our shirts. I'll just abbreviate it. This is our skirts. And this is our, what did I say? Shoes, right? No, I don't want SH again. I'll do SHO. I don't know, whatever. All right, so how many shirts first. How many shirts do we have? 3. How many skirts do we have? 4. And how many shoes do we have? 5. And the fundamental principle of counting says that if we multiply these together, this will be the total number of different combinations of outfits that we have. So what is 3 times 4 times 5? 60. There are 60 outfits here. Now, do some of them look a lot like other ones? Well, of course they do. But there are 60 different outfits. Okay, here's another example. We have 6 favorite stores in the mall, and how many ways can the following happen? We only have time to go to 3 of them. Well, if I only have time to go to 3 of them, I only need 3 bars. And we're assuming things like it doesn't matter what order, not necessarily it doesn't matter what order, but it doesn't matter if we're backtracking. That's how I should say. Like that's an excusable thing that's okay, right? So if I go to this store and then I go over here to this store and come back to this one, then that's an okay thing for us to do. We're not trying to minimize our time or something like that. So how many options do I have to choose to go to the first store? 6. I have 6 different stores that I enjoy going to when I go to one of the 6. But we don't go to the store and then leave the store and then walk back in. That's not what we're talking about, right? Once we leave the store, we're done at the store. And how many stores do we have to choose from now? 5. And then 4. And we are going to multiply 6 times 5 times 4. 120. There's 120 ways that we can choose to go to 3 of these stores. It's a lot of choices, actually. 120 ways. What if we're going to go to all 6 of them? Well, then I would write down 6 of these lines. Option for store number 1 would be 6. And 2? 5. And then 4. And then 3, 2, and 1. And the fundamental principle of counting says, okay, multiply them all up. 720, that was the number we had from before when we did the one-to-one correspondences with 6 items. It's 720. 720 ways for this to happen. Okay, our last example. And I'm going to write one down, and then I'm going to make you do it, and we're going to see if anybody will be willing to share. We're going to create a real-life example of the null set in your life. Real-life example of the null set in your life. So this is the one that I'm going to create right now. This is the set of, right, so I'm going to do a curly brace. This is the set of the infants in my home. This is the null set, because if I were, let me give it a name. Let's call it the set I. This is the null set, because if I were to be counting it, I would find that this number is 0 in my home. Write one down for your life. Now notice what I didn't write inside the curly braces. I didn't write the phrase the number of. It's not a number of. It is a description inside those curly braces. So write a description of a real life null set in your life. Somebody share with us. What'd you write down? What do you have?
Soccer games I have played.
Soccer games you have played. So I assume you're not a soccer player. Okay. So soccer games played. It's a good one. Somebody else?
The number of siblings in my life.
Siblings in your life. You're an only child. My mother was an only child. She would have been able to write that one down too. I wouldn't be able to write down soccer games, but if I said past about age 5, I could go with that one. What's another one? One more person.
Oh.
What do you have?
Number of trash in my room.
Oh, you're a clean person. That's wonderful. That's excellent. So trash in your room. Okay. If there's no trash in your room, it would be an empty set. Excellent. Okay. So you've all got something written down.